Hello everyone, I'm Weida Hu from University of Science and Technology of China. I would like to thanks to the organizer for this opportunity to present our recent work. The title of my talk is Lyman Alpha Protocluster Redshift 7. Here are my collaborators, including Junxian Wang from USTC, Sangeeta Malhotra, and James Rose from Goddard Space Flight Center, Jian Zheng from Shanghai Astronomical Observatory, Leopoldo Infant from Las Campanas Observatory, and Felipe Barrandos from Pontificia Universidad Católica. So this is the outline of my talk. First, I will introduce a little background about realization and the Lagrange survey, and then I will present the discovery of a protocluster at redshift 7 and its properties, and last I will summarize my talk. Roderick has gave a very nice overview of clusters and the protoclusters, so I'm going to skip this slide. The epoch of realization is when the hydrogen in the universe transitioned from neutral state to ionized state. The cosmological theories tells us the universe began with a Big Bang at around 40 billion years ago, around 400,000 years later, the neutral hydrogen formed and filled the intergalactic medium. This epoch is called Dark Ages because it was opacity to the high energy photons. The emergence of the first generation objects like such as the stars, galaxies, and quasars marks the end of the dark ages in the cosmic history. The ionizing photons were released by these first objects to the intergalactic medium and ionized the medium. This epoch is very important for the cosmology and the formation and evolution of the galaxies and large-scale structures. So Lyman alpha emitters are powerful probes to investigate the epoch of realization. When the Lyman alpha photon emitted by the galaxies passed through the intergalactic medium, it will be resonance scattered by the intergalactic medium, and the observer spectrum will show some signals of this process. So if, for example, if we put a Lyman alpha emission line with a Gaussian profile, the result spectrum shown as this solid line will be highly asymmetric, and the peak will be redshifted. So by comparing the observer properties of the Lyman alpha line with the intrinsic properties, such as, for example, the Lyman alpha luminosity or the Lyman alpha velocity offset of the peak, we can infer the IgM neutral, the neutral hydrogen fraction in the intergalactic medium. So we carry out a narrowband imaging survey to search for Lyman alpha emitters, named Lyman Alpha Galaxies in the epoch of realization. We designed a narrowband filter to search for Lyman alpha emitters at redshift 7. The filter was optimally designed to avoid the sky transmission curve and to avoid strong sky emission and atmospheric absorption. The red line in this plot shows the transmission curve of the narrowband filter. Its central wavelength is around 9,642 angstrom, and full width at half maximum is about 192 angstrom, corresponding to Lyman alpha emitters at redshift 6.89 to 6.97. The filter was installed on the dark energy camera on CTIO Blanco 4-meter telescope. The dark energy camera has a very large field of view and a red sensitive camera. Its total response at 9,642 angstrom is still larger than 15%. This combination makes NAGR is one of the most efficient survey in searching for Lyman alpha emitters in the Epoch of Reionization. So we aim to construct a unique narrowband selected Lyman alpha emitter sample at redshift 7. We expect to find more than 600 Lyman alpha emitters. The area coverage will be larger than 20 square degree. We adopt a wedding cake strategy to cover both bright and to discover both bright and faint Lyman alpha emitters. Based on this Lyman alpha emitter sample, we will study the properties of the high redshift Lyman alpha emitters, such as Lyman alpha luminosity function, the stellar population of these galaxies. We will also constrain the cosmic realization by the by the evolution of the Lyman alpha luminosity function and the clustering effect of Lyman alpha emitters. And we can also find early large-scale structures. So up to now, we have observed 4 fields: cosmos, Chandra deep field south, gamma, and wide field. We have selected 174 Lyman alpha emitters at redshift 7 in these 4 fields, and our recent result shows the neutral hydrogen fraction at redshift 7 is smaller than 0.33. So the protocluster region firstly shows some interesting signal in 2070. In 2070, we selected 23 Lyman alpha emitters based on 34-hour narrowband exposure in the cosmos field. Here I show the spatial distribution of the 23 Lyman alpha emitter candidates. The size of the circle indicates its Lyman alpha luminosity. If you focus on the luminous Lyman alpha emitters, you can find that Lyman alpha emitter 1 and 3 is very close. The distance is only 3.6 arc-minute, corresponding to 9 megaparsec. Their luminosity are larger than 10 to 43.3 erg per second. The bottom show the pseudo color cutout of these 2 Lyman alpha emitter. The Z band is blue, narrowband green, and wideband red. They are very green and compact. So these 2 Lyman alpha emitter were later spectroscopically confirmed by Magellan observation. Their high signal to noise ratio spectra show the obvious asymmetric profile and small the velocity velocity offset between these 2 Lyman alpha emitter is very small. Such numerous Lyman alpha emitter ratio 7 is very rare. Finding 2 bright Lyman alpha emitter in such close distance is very interesting, indicating they must be physically linked. So we decided to take more narrowband observation on this field to figure out the physical nature of these 2 Lyman alpha emitter. In 2019, we obtained 47-hour narrowband exposure in a cosmos field with the help of developed data reduction pipeline and a deep broadband image by Observable HIC camera. We selected 49 Lyman alpha emitters in this field. So this plot shows the spatial distribution of the Lyman alpha emitter, and the contour shows the galaxy number density. So you can see overdense region in the left part of this field. It is identified as a protocluster redshifts 6.9 with overdensity of 5.1. This is zoom-in Lyman alpha emission spatial distribution plot. We carry a spectroscopic follow-up using Magellan Telescope and the red symbol of are the red symbol in this plot are the member Lyman alpha emitters of the protocluster, and the field symbol in this plot are the spectroscopically confirmed Lyman alpha emitters. For the 14 Lyman alpha emitter from Hu 2019, 11 Lyman alpha emitters was spectroscopically confirmed. The bottom figure shows some example spectra of Lyman alpha emitters. The volume of this protocluster is 66 times 30 times 26. The overdensity is around 5.1, and the line of sight velocity dispersion is about 800 kilometer per second. So we use several methods to find as much number Lyman alpha emitters of the protocluster as we can. Firstly, we four lower grade Lyman alpha emitters were identified by the spectroscopic spectroscopic observations, as shown as the red triangle in this plot. Secondly, we note the transmission curve of our narrowband overlaps with the HIC narrowband. So we started the two narrowband image and selected three more faint Lyman alpha emitters, as shown as the squares in this plot. In total, we discovered 21 member Lyman alpha emitters for this protocluster, and 16 have been spectroscopically confirmed. So according to the spherical collapse theory, we calculate the linear overdensity of this protocluster is 0.54 at ratio 7, and the linear overdensity is proportional to the time to the 2/3, so it will exceed the critical value for collapsing at ratio of 2. In other words, this protocluster will collapse into a cluster at a redshift lower than 2. If we assume the matter within this protocluster region will collapse, the present day mass of the cluster will be 3.7 times 10 to 15 solar masses.